Boost converters provide an adaptable solution to stepping up DC voltage in many applications where DC voltage needs to be increased without the need to convert it to AC using a transformer and then rectifying the transformer output. Boost converters are step-up converters that use an inductor as an energy storage device to provide an additional voltage to the voltage input source. In certain applications, such as an electric vehicle, which requires about 500 volts, a boost converter can be used to increase the supplied voltage and eliminate the need to acquire a large 500 volt battery. Another advantage of using a boost converter is that it can extend a battery's life by boosting the battery's low output when used for a long time. Let's take a quick look at a simple boost converter circuit. As you can see here, it has the same components as a buck converter, which I spoke about in my previous video, with a slight variation in how the circuit elements are placed. We have a DC source on the far left, which usually represents either a battery or a rectified AC voltage. This provides the signal we're looking to boost. The next component is the MOSFET. This MOSFET is used as a switch to control the direction of current in the circuit. It also has a PWM signal connected to its gate to toggle the switch. Now, if you're not sure of what a PWM is, a PWM or pulse width modulation signal is a square wave that has a variable duty cycle. Let's say we have a square wave with 50% duty cycle, meaning the signal is high the same amount of time it's low. PWM signal can have a duty cycle of 25%. This means the square wave will be on 25% of the time and off 75% of the time. Or it could have a duty cycle of 10%, meaning the signal is high 10% of the time and low 90% of the time. We will later find out that the duty cycle of our PWM signal will play a vital role in the output voltage of our boost converter. The next component is a forward bias diode. This diode is placed in forward bias to force current induced by the capacitor to flow to the load alone and not back to the inductor. Last but not the least, we have the capacitor, which stores charges and ends up having the boosted voltage across its nodes. And finally, the load, which simply makes use of the voltage that has been provided. If you're finding this video valuable, hit the like button. Also, I make electrical engineering tutorial videos like this one, so be sure to subscribe and hit the bell for notifications so you never miss a video. Let's get back to it. Now we'll analyze how the circuit works. The circuit operates in two states, which are derived from the ones and zeros of the PWM signal. We'll talk about the on state first of all. For the on state, the MOSFET conducts and closes the loop between the inductor and the power supply. The left-hand side of the inductor, which is now connected directly to the voltage supply, is positive, and the right-hand side is now negative, which means that the current in the inductor will be flowing from the positive to the negative terminal, or the left to the right. During the on state, the power source supplies currents to the inductor, which stores energy in its magnetic field. Now all the current flows through the MOSFET back to the voltage source and not through the diode. This is because the collective impedance of the load, diode, and capacitor are much larger than the short created by the MOSFET and will allow current to flow through the path of least resistance. Now when the MOSFET switch is open, current flows from the source to the diode. The voltage of the source will be seen at the anode of the diode. There's also a sudden drop in current in the circuit when the switch opens. This sudden drop in current produces a back EMF as the stored energy in the inductor's magnetic field induces a current. This back EMF will also be seen at the anode of the diode. The total voltage at the anode will therefore be the back EMF produced by the inductor plus the input voltage. This higher voltage forward biases the diode and charges the capacitor to Vin plus VL, excluding the diode's voltage drop, typically around 0.7 volts. Now each time the MOSFET conducts, the cathode of the diode is more positive than its anode due to the charge on the capacitor. The diode is turned off and the capacitor and the load are isolated from the circuit. However, the load is continually supplied with Vin plus VL from the charge of the capacitor. Although the charge on the capacitor depletes during this period, the capacitor is recharged each time the MOSFET is switched off, thereby maintaining a constant voltage supply to the load. Based on this reasoning, we can infer that the output voltage depends on how long the capacitor can charge, which happens when the MOSFET switch is turned off. In other words, when we lower the duty cycle of our PWM signal, we can have a higher voltage at the output. The output voltage can be calculated as Vin divided by 1 minus D, where D is the duty cycle and Vin is our input voltage. Now in certain cases, we may need to reduce the voltage instead of increasing it. If you want to know more about that, check out this video where I talk about the buck converter. Thank you for watching this video, and I'll see you in the next.